Hi, I'm Ryan Stortz, and this is Rattle. Our agenda for this evening will be a light dusting of Ethereum smart contracts that Patrick didn't fully cover. I should mention that Patrick and I did coordinate a little bit, so this won't all be a repeat. We're going to follow it with some Ethereum VM internals, then end with a bunch of information about SSA construction and analysis. So where do I click? There we go. As I said earlier, I'm Ryan Stortz. I'm a principal security engineer at Trail of Bits in New York, and I've been kicking around the industry for about 10 years, and I've spent far too much time playing capture the flag competitions. So at CanSec earlier this year, a coworker of mine, Jay Little, and I presented a talk called Black Hat Ethereum. That talk was meant to introduce Ethereum and specifically binary EVM analysis to more traditional security people. In the first half of that talk, we covered identifying and extracting contracts from the blockchain. And in the second half, we demonstrated several ways to analyze these binary contracts, how to identify vulnerabilities in them, and how to write an exploit and place it on the network. As part of that talk, I briefly demoed Rattle, but it wasn't quite ready for prime time, and I wanted to do a more in-depth talk, and that's this talk. So Ethereum smart contracts. So normally this is where I would introduce them, but Patrick just spent an hour, 20 minutes explaining Ethereum smart contracts. So in this case, I'll take the opportunity to explain exactly what an ICO token is and how it works. It took me a while to grasp what it is. So an ICO, initial coin offering, is the cryptocurrency's world's equivalent of initial public offering. It's the first time a share, in this case represented by a token, of a company is available for public sale. So, and how that works is it's actually implemented via a contract interface or protocol. They're normally a sale of this ERC20 style token. ERC is like Ethereum reference, Ethereum RFC. And the ICO organizers normally sell these tokens for Ethereum and then quickly sell that Ethereum for USD or whatever local currency they work in to actually fund their startup or their product. The ERC20 is like an ABI level specification, and contracts that implement a token are expected to implement transfer from, right here where you have from and to and the number of tokens, and you get a success back, maybe, if people implemented that function right, which they don't. But what does this all actually mean? What is a token? Where do I get a token? What does it look like? Well, it doesn't look like anything. A token is actually just an entry in a hash map with your address and some amount of value you have, like an integer value of how many tokens you have. And it just is in the persistent storage, and everything's managed through this interface. So if you actually wanted to see or query how many tokens you have to call the right contract's balance of with your address. So most people use Firefox or Chrome plugin to interact with these things called MetaMask, and the exchanges, have more node-based systems normally that can interact and trade on these ERC20 tokens. And I guess the joke here is the exit scam isn't normally encoded into the contract itself. They just kind of take off. So I don't really want to explain ICOs and have people jump into them without knowing that there's a lot of risks involved. Most of them are scams. This is a report published in April, and this tracked all of the ones that have more than $50 million in market cap. Market cap number itself is a scam because it's just like the number of shares they issued multiplied by the most recent sale price of even one token. 81% of them were complete scams. Of all of them, only 8% moved on to trade, and 1.6% are marked promising, and those people are here and they're sitting over there. They're wearing purple shirts. You can talk to them about their thing. But yeah, like, be careful. And additionally, most of these ICOs are technically securities. If you want to argue that, you should talk to them. The Canadian Securities Administration or the US SEC will come knocking if you run one, or possibly even if you invest in one. So back to the Ethereum VM. So the Ethereum VM is a Harvard stack machine. Stack machines are pretty easy to implement, which is why they chose this. If you're familiar with a RPM, like a reverse Polish notation calculator, that's how they operate. The programs written in EVM run on every client as they validate or the blockchain or mine new blocks. Patrick used the phrase world computer. I have it in my notes too. Yeah, so they run on the world computer, and storage and execution length is limited by the gas charge for each instruction. And this is how they allow you to use a Turing-complete language, because they just limit the amount of instructions you can retire based on the amount of money you can put in. And the gas costs need to pay for persistent storage and the execution of these contracts across everyone's computer, which actually ends up going to the miners. But so I would argue that EVM is a Harvard architecture with 6 address spaces: code stack, call data, the arguments, storage, memory, and the return data. It has a native 256-bit data width, and there are many, many duplicate opcodes. So for a quick refresher on a stack machine, I have a little diagram we can walk through. So first one here, we're pushing number 2. Pushing number 3, add takes 2 arguments, so they are popped off, added together, and results pushed to the stack. We push 8 in this case now, and then we issue a mul, and the same idea: 2 arguments multiplied, result pushed to the stack. And this is how the whole thing works. This looks pretty familiar to Patrick's slide. There are many EVM opcodes, but not all of them are created equal. Some are better than the others. So the jump by, return, like, they're not security relevant, but they obviously can define control flow. Revert and invalid are exception causing, so they're on the true side of asserts. The interesting ones here are actually call data size, call the data load, which are the argc and argv of the Ethereum world. SStore and SLoad, they manipulate persistent storage. And then these bottom 4, call code, delegate call, and self-destruct. So call code, and delegate call allow you to call into other contracts. So the way libraries are implemented in Ethereum is they're actually existing at another address, and you're supposed to do an external call into them. And that has gone horribly wrong in several ways. Like, the biggest one is, I think, $90 million in Gavin Wood's Ether was locked up because somebody took over one of these library contracts and killed it with the self-destruct. Self-destruct destroys the contract. You can never use it again, and it returns all of its stored value to whoever you pass as an argument. So if the contract doesn't have call code, delegate call, or self-destruct in it, there's actually no way to get any Ether out of that. And older contracts, you could send Ether to them, and it would be trapped forever. Newer ones have a little bit of protection against that. So in our EVM analysis, we wrote a Binary Ninja plugin, and also an IDA plugin, called Ethersplay, that does graph-based assembly of Ethereum. I just want to go a little bit into this. I know Patrick covered a little bit. So we enter the dispatcher, and the first few things we do here are push 60 and 40, and then this mstore. So this memory offset 40 is what they call the free memory pointer. And they're setting it to 60, which is the next available slot. So this kind of works like the old SBRK instruction or interrupt in Linux and the BSDs, where it's just like a new high watermark every time. It like gives you a new slab. We check to see if your call data size that you send in is less than 4, and if it is, you branch to this like fallback default function. Then if it's if you have specified a 4-byte function hash, it starts switching them on that switch that Patrick was talking about. So the point of showing you this, though, is showing you how difficult it is. Like, do you know how many arguments mstore takes, or what it does? Like, does it take 2? Does it take 1, and does it return 1? Stack machines are just incredibly difficult to reverse engineer because there's nothing you can name, and you have to keep a scratch pad of everything. So that's where I wrote Rattle. And I don't know what this graphic is. Oh, you can't see it. It's good. It's like a weird eyeball in the distance. Patrick mentioned single static assignment form. And to discuss Rattle, we have to talk about it a little more. In computer architecture, the instruction set architectures can be broken down in a few groups, like stack machines, like old Lisp machines, register machines, register file machines, and file machines. Almost every real CPU is a register file machine where there's a limited number of high-speed registers like RAX, RCX, etc., and then also direct memory accesses in a lot of their instructions. And the limited number of registers, causes the compiler to spill them out of the stack, and you end up using a lot more of the stack. And this is why I generally find it's easier to reverse 32-bit x86 than 64-bit x86, because you can name things. But what if we had an unlimited number of registers, and then we could avoid that scratch storage, and then also every time you assign one, you just give a new value. Like, who cares what %0 was back, so long ago? I'm like on %100 now. If you do that, you get the one single assignment feature, which provides like an implicit level of data flow. So the goal with starting to convert EVM stack machine into the goal was to convert EVM stack machine into SSA form. And rather than jumping right in to like writing the code, and I decided to do a literature review. And I could not find anything that lifted a stack machine into SSA. This is the best paper I found, Simple and Efficient Construction of Single Stack Assignment Form, which was more towards when you already have a control flow graph and you're working with some sort of intermediate language. Java, there's a couple Java-related papers, because Java is also a stack machine, and they definitely did SSA form on Java, but then the papers are about the analysis they did on the SSA form, not on constructing the SSA form. So I couldn't find a good algorithm on it. So to identify blocks, so I had to jump into my own. To identify blocks, I used I was going in like, yes, I have to use the superior recursive descent technique. Like being forward thinking, like what if contracts jump into the middle of instructions, and I have to be able to support all of these like potentially malicious contracts. Recursive descent is a work list-based algorithm, and I have this isn't exactly the real code, I cut it down a lot. You start by adding your first work item to the list, and then just loop until your work list is empty. And in the case of Ethereum, when you encounter a jump, you end the processing of that block, and you append its target if it's resolvable. If you hit an indirect jump, or the conditional jump, you add both. And then you just loop forever. The problem here is you have to trace the stack to identify jump targets, and additionally, not all jump targets are in the current basic block. So then you have to resolve parent stacks. And And to address this, I took the approach used in scripting languages for scope resolutions. If you've ever written your own scripting language, you kind of like have this like scope chain where like I'm gonna check the local scope and then like the one higher scope and then the global scope. So if, for example, a dup12 instruction will duplicate the 12th item on the stack. But if your stack pointer is only at 7, it's going to look at the parent scope for the 5th item. And if it doesn't have a stack of 5, it'll go further. And you just go up the stack until the value is resolved. While I was initially pretty happy with this approach, it turned out to be pretty problematic. For example, how you resolve your parent stack if your control flow graph is incomplete. So you get into a lot of fun control flow graph recovery issues. Yeah, so in this process, I was thinking I could identify the blocks, link the blocks, trace the stack, replace EVM instructions with the SSA instructions, and then skip any dup, swap, pop, or push, but still perform their stack operations. And then I would like win and I'd be done. But no, Ethereum had other plans. So EVM doesn't actually support internal subroutines. There's no internal call or internal return. There's only external call and return. So the Solidity developers and the Viper developers get around this by pushing a return address onto a stack, and then several blocks later, indirect jumping back. This is fine if only one function calls that internal function. If multiple functions call it, then you have a lot of control flow problems. So my example here is function 1, pushes 10, which is the return here, pushes 40, jumping into the inline function, which in this case just loads the storage at 0, and it jumps back. I also have function 2 doing the same thing, and it jumps back. But if you don't reprocess this block, you end up with function 2 flowing into 10. If you do reprocess the block, then you have an over-approximation of control flow because function 1, in theory, could flow to 30 because it's not context sensitive or path sensitive. So that caused me a lot of problems. So instead of going with recursive descent, I went with linear sweep. Like I actually backed up and did linear sweep. And why? It's because the yellow paper actually defines control flow as only being able to go to valid jump targets. So this is actually Patrick's slide that I put in my slide deck before his branding. Like you can only land on a jump target or a jump dest. And I actually went and looked at the parity and Geth code, and they do enforce it. So linear sweep is actually fairly viable here. So this time, we initially identified blocks with the simpler algorithm. If we hit a terminating instruction, we end the block. If we encounter a jump dest, we start a block. And if our terminator is a jump I, we start a new block at PC +1, and then we link it in. And next, we trace the blocks. We trace a stack and link in any indirect jumps that are immediately resolvable, like where the target is pushed in the same block. And then, but we still have the same problem because I'm still trying to resolve blocks with or values up their scope chain. So then I have this 3rd/9th and final attempt, which is I discovered that the maximum stack size is 32 entries. So if I start by pre-filling all the blocks with unresolved placeholder values and then lifting them that way, I can process them all in isolation and then link them together later. And then I will discover the edges out of band and like restart when new edges are found, because otherwise my file resolution goes crazy. So I actually have like a little walkthrough of like SSA recovery on some random function I grabbed. So our first instruction here is jump dest. There's no reason so on the left here is the EVM. On the right is my pre-filled stack, which is only like 8 or 9 deep. In the middle, we're going to have our SSA form. So jump dest has no need in an actual, it's just noise. So our first thing is caller. Caller takes no arguments and returns a value. Our stack has %0 on it. We dupe, which you can see, yeah. We copy stack slot 2 to stack up and then push it on the stack. We push 0. In the first pass, my pushes are still values. Later, they become concrete values during optimization. We call add. So add's the first one that pops 2 things off the stack, and then in this case, it grabs one of these unresolved stack pointers that's something that's passed in from a parent block or dominating block. And then jumping ahead a little bit, we end up with this. So we slowly start to build this out, and you can actually say like, oh, well, it's clear to me now that %2, the result of this add is actually the storage address we're loading from. So to finish lifting this SSA form, I end up with this intermediate step where this is from a dispatch. I have these unresolved stack pointers and the blocks they're unresolved in, and to resolve them and to generate phi block instructions. So phi is like a annoying thing that's implicit in SSA form. It basically says I need to combine these 2 values, and it's whatever one has been updated most recently, or is actually specifically on the path that you came down. So in most compilers, like they optimize until they stop optimizing, and resolving phis and resolving values is the same way. While it's still changing, you keep changing it. So it makes that algorithm fairly straightforward. Once we have our full SSA form, we can do fun things like constant folding. So this is the constant folding algorithm I have. And you can see here that if I have 2 constant or concrete arguments, and it's an exponentiation, I just calculate the exponentiation, and then, where is it? Right here. I replace all of the uses of that value with that new result, and it removes the exponentiation completely. I call it readers. Most people call it users or uses. So that tweet that Patrick posted in his slide here, after constant folding, becomes this. So in this and right here is actually just an indicator that the value stored in the storage 3 is an address. So it can even be optimized more, where now, after the screenshot, I just remove this and as well and have a comment here saying that storage 3 is an address. We can also trivially compute def use and use def graphs. So this is actually from when I was debugging kind of insane control flow bugs. So this is not real. I was trying to graph this 1052 and see why I was getting like weird control flow. And I'm propagating through my phi node. So a jump should only be, Solidity doesn't calculate its jumps. They're always constant in my experience. So these 2 right here are the actual jump targets. This right here, like the result of this and or these memory loads, they're just wrong. And you can see like there's weird connections here. Like for some reason this 1044 ends up in this phi, and there's another issue over here. And I like this graph because I was able to actually debug and fix this bug. But it is trivially possible to make these graphs now. You can also do memory and storage recovery. So with a binary contract, I can run this King of Ether, which is a well-known one that got hacked or had bugs early on. And I know that it uses storage values 0 through 6, and you can use the Web3 Python or even JS libraries to query what their current value is on the blockchain or even at old transactions. You can also check to see where your contract can send Ether from. In this case, this example can send it in 3 areas, and we actually have hard-coded ETH values. So this is like 100 billion way or something, which is like the basis unit of Ether, which ends up being 1.0 ETH, and this one's 10. And you can know those are where that's called from. We can additionally trace loads from call value 0 or call data load 0 and taint them and find comparisons against their function hash and split those functions off and recover the ABI of these individual functions. And then once we split them off, it's trivial to find out if they've been marked payable, which means they're able to receive Ether, or if they're marked as they have some modifier that's common, like only owner. So I have a demo. Let's hope the demo goes well. Oh, that's not the right screen. Mirror. Here we go. So Rattle is in Python 3, which upset my coworkers, except for not as much as when I first wrote it. It was in C++. And so I'm running on the King of Ether, and I have the optimizer turned on. So what it does is it dumps everything to the screen and then generates a bunch of GraphViz files. And we have things like this number of monarchs function. It uses storage. I'm using PNGs rather than PDFs. It uses storage at offset 6, and we've got just these handful of small blocks. So this actually says, I'm going to check the call value sent to me. If it's 0, then you can enter, right? So this function you should never send Ether to it. It'll instantly revert, and this is a protection against contracts eating Ether. And if you do, if you don't, then you can call in we will return the number of monarchs. That function in Ethersplay, I grabbed the wrong example. It's this big, but either way, it's not 6 instructions. I was supposed to grab this one, transfer ownership, which is here. So this one has the same not payable, and then this guy right here is checking the storage of 0, which I've marked as an address because I did a mask against it, and the caller, and it's comparing them. So this right here is an only owner check, making sure only the contract creator is able to modify it, and in this case, it transfers ownership. And if you are, they do this thing where they do an equal and then a bunch of is-zeros for some reason, so it's inverted. They actually update it, right, with the s-store of 0. So with that, you can do a lot of neat analysis on on your compiler output and on other people's stuff in the blockchain for any reason that you'd like. So releasing Rattle. So Rattle is in private beta right now. If you click this link, or in 2 minutes, I have a scheduled tweet going out with that link. You can request an early preview of that in our Solidity Static Analyzer. It will be released to GitHub on the Trail of Bits, and you should check our Twitter for its release. That is my talk. Are there any questions? This always happens to me. No one has questions. Is this going to be another Win disassemblers question, Detmar?
No, I know what a decompiler is. Hey, so what's the licensing like?
So this is a point of contention between me and Dan. I would like to release it under Apache 2, but it might not be. And that's all I'm going to say about that.
Any other question? Okay, then thank Ryan again for his talk.